Okay, let's take a look at motion from a graphical perspective. If, say for example, I accelerate from 0 meters per second to 25 meters per second in 5 seconds. So I go from 0 meters per second to 25 meters per second in 5 seconds. How can I understand that in terms of displacement or distance I travel through during that time, and also the acceleration or the change in speed during that time, during those 5 seconds? Let's take a look. Let's first look at speed or velocity. Okay, so this occurs over 5 seconds. And the speed is 25 meters per second. So if I start at 0, I'm going to have a point at the origin, and I'm going to have another point out at 25 meters per second in 5 seconds. I'm just going to draw a line connecting the two. Oops, what happened here? Line connecting the two. There we go. And that defines this triangular shaped region to this point. And if I wanted to find out what the acceleration of this was, what I would do is I would find the slope. So I'm going to draw another graph right under it, and the t-axis is coincident. So these are the same axes, right? This is 5 seconds here. And to find the acceleration, what I'm going to do is I'm going to find this slope. So the acceleration is v final minus v initial over the time elapsed. So 25 meters per second minus 0 meters per second over 5 seconds. So 25 meters per second over 5 seconds is 5. Now a meter per second is also a meter per second squared. So our acceleration in this instance is 5 meters per second squared, which means that if I were to observe this from 1, 2, 3, 4, and finally 5 seconds, what I would notice is that after 1 second, I would be at 5 meters per second. After 2 seconds, I would add another 5. I'd be at 10 meters per second. After 3 seconds, I would be at 15 meters per second. After 4 seconds, I'd be at 20 meters per second. And finally, at 5 seconds, I'm at 25 meters per second. So the acceleration is just the amount of velocity that's added to your motion for every single second that passes. Okay, so if I'm going to plot this, notice that this is a straight line. So what that means is the slope is the same at every point. So it's a constant. So graphing a constant is just a straight horizontal line at 5 meters per second squared. Okay, so we found our acceleration. Let me go back and find our change in position. And again, this time axis is going to be coincident. Okay, and what I'm going to do is where the acceleration was the slope, we found it here. The displacement or distance through which you travel in moving from 0 meters per second to 25 meters per second over those 5 seconds is going to be the area of this triangular region. So we're going to find how far we are from where we started after 5 seconds when starting from rest, 0 meters per second, and adding 5 meters per second to our velocity every second for 5 seconds to wind up at 25 meters per second. Let's do that. So my position and the area of a triangle is 1/2 base times height. If this was some other area, I'd use the appropriate formula for the area, but this one happens to be triangular, so I'm using the area for a triangle. So we have 1/2 times 5 seconds, and the height is 25 meters per second. So 5 times 25, first of all, the seconds cancel, leaving us with meters. And 5 times 25 is 125, and half of that is going to be 62.5 meters. So out here at the 5-second mark, notice all the time axes line up as we're doing this, right? At the 5-second mark, I'm at 62.5 meters. Okay, good. But I would also like to know, maybe I'd like to know the shape of this. Well, at time 0, I'm at the origin. Maybe I would like to know at the halfway point. So let's see. At the halfway point, it's exactly 2.5 seconds. So 1/2 base times height is 1/2, 2.5 seconds. And right here at 2.5 seconds, I've been adding 5 meters per second, right? So at 2 seconds, right, I added 5 and 5, so we would be at 10 meters per second at 2 seconds. At 2.5 seconds, I'd be midway between 10 and 15, or 12.5 meters per second. Okay, so let's figure out what that is and get rid of my previous calculation here. Okay, so 2.5 times 12.5 is equal to that, and then I'm going to divide that by 2, and I get something like that, 15.625, which is 15 5/8 if you know your fractions. So I'm going to just write that as 15.625 meters. Okay, so that is roughly 1/4 of the 62.5 meters. Okay, so that's a point right around here. So this is 15.625 meters. I'd like everybody to notice that this is not a straight line, right? So if I do this, I get a sort of a curve. This is a parabola. You'll also notice that in the first half of the time, we move through only 1/4 of the distance. In the second half, from 2.5 seconds to 5 seconds, we move through the remaining 3/4 of the distance. What that means is that we're accelerating. For every second that passes, we go through ever greater distances. Okay? So you guys will be asked to do one of these problems. The numbers will be a little easier, but just remember, if you want to find the distance traveled, it's the area and from the velocity time graph, otherwise known as the VT graph. And if you'd like to know the acceleration or the rate at which the velocity changes, you just calculate the slope. Everybody has calculated the slope in your math class, so this should be no big deal. By the way, what we were doing is actually what Newton did. And if you're going in this direction, taking the area, that's called integral calculus. And if you go this way, it's called differential calculus. No calculus will be required on the exam. Don't worry, remain calm. Okay, just think of it as the area and the slope, and you'll be fine. Okay, just a couple of additional points. If you're calculating, well, let's do Newton's laws. The first law, law of inertia. An object at rest tends to remain at rest, and an object in motion tends to remain in motion at a constant speed in a straight line unless disturbed by an external unbalanced force. We could also say tends to remain in motion at a constant velocity unless disturbed by a net force. So inertia is that property of matter that makes matter reluctant to change the way it's moving. Motion we really describe in terms of change in velocity or acceleration, and net force is the sum total of all forces acting on the object. In the second law, this is the only law that can be described in an equation, only one of Newton's laws that can be described in an equation. The net force is equal to mass times acceleration. So for example, if you have a box sitting on the floor and you have a force this way and you have a force this way, this one is 200 newtons and this is 100 newtons. The net force is equal to 100 newtons minus 200 newtons or minus 100 newtons. The negative sign tells you which way. My usual sign convention is that negative means to the left. So notice that the net force is in the direction of the larger force. Okay, if you're solving this, you could refer to the visual calculator. I've shown some of you guys as a check on your algebra. It is no substitute for algebra, so please, I don't want to see this as proof that you did the math right. But just know, if you want to find force, cover that up, cover the F up with your finger, and what remains is M times A. If you'd like to find A, cover the A up with your finger, and it's F over M. And if you'd like to find M, cover the M with your finger, and what remains is F over A. Okay? Force is in newtons, mass is in kilograms, and of course acceleration is in meters per second squared. Okay? So mass and force are directly related, as are acceleration in force. So that means if I apply more force, it can move more mass with the same acceleration. For acceleration in force, if I apply more force with the same mass, I can get more acceleration. So you'll notice the variables change in the same direction. More force can cause more mass to have the same acceleration. Okay, inverse. We have an inverse relationship between acceleration and mass. So if I keep the force constant and I increase the mass, I will have less acceleration for the object. If I decrease the mass, I will have more acceleration for the object. They change in opposite directions. Okay, so here if one variable increases, the other one decreases. Here if one increases, the other one increases, and also if one decreases, the other decreases. Okay. Third law. For every object, there's an equal. For every object, a reaction is met with an equal and opposite reaction. So if I'm standing on the floor, I push down on the floor with a force equal to my weight, but the floor also pushes back on me with a force that's equal but opposite. Okay? These don't add together to form a net force because they act on different objects. One acts on me and one acts on the floor. So for every action, there's an equal and opposite reaction. If the third law didn't exist, and say I was standing on the floor, I would pass right through the floor as if it didn't exist, maybe because the floor wouldn't exert an equal and opposite force back on me. Okay, so you could see why not having the third law would be a bit of a problem. And also, why, even though it's a little hard to understand, why it's necessary, and without it, the first two laws really don't matter, because these net forces that cause the changes in motion really wouldn't be able to be communicated between objects. Okay, so third law, very, very necessary. For every action, there's an equal and opposite reaction. Okay, so let's see, did I miss anything? So you guys should be able to name and talk about the three laws very clearly. Know the difference between mass and weight, right? If I wanted to lose weight, I could just go to the moon, and I would lose approximately 5/6 of my weight. However, my mass would be unchanged, because weight near the surface of the Earth, as you recall, is your mass times the local gravitational field. Okay? So know that weight is a product of mass and gravitational field, and mass is just a property of matter. Mass is the same any place in the universe. Weight is the product of mass and gravity. So if we were to have a Venn diagram, and this were mass and this were gravity, that means that weight would be the overlap between the two, and you must have both to have weight. If I go to another planet and the gravity changes, I have a different weight, but the same mass for that reason. Okay? I hope everybody understands that. Know that also for the second law, if the net force is 0, that means that you're not accelerating. It doesn't mean you're not moving. Okay? Think of not moving, a velocity of 0, as one of many possible constant velocities. Okay, Newton commented on changes in motion, acceleration. He never really commented on constant speed motion. Okay? Okay, I hope that helps. Review some of the online stuff. Bring your packets with you, and you can staple your sheets that we did on graphing to the back of that. You can use that as your reference on the test. You can only use your packet. Put your name on it. Okay? You can't have a community packet. So I expect you guys to come to the test prepared. Okay? Okay. Good luck. See you soon.